Hello again, physics friends. We're going to do a practice problem here that allows us to flex the muscle of how to do problems with rear clock set ahead / relativity of simultaneity. So we have the question in front of us. Alice stands at rest on the ground, and near her are 3 clocks. The clocks are all synchronized and at rest in the ground frame. Okay, so Alice and all the clocks are not moving relative to the ground. Clock B is 30 feet to the right of clock A. Clock C is 60 feet to the right of clock B. Okay, so we have clocks A, B, and C on the ground and Alice on the ground. Now Bob runs to the right at speed 1/5 of C relative to Alice. So we're being asked now to draw diagrams showing the situation in both frames. So we want to draw snapshot diagrams in Alice's and Bob's frame. And then in Alice's frame, we're told that clock B reads 0, the middle clock reads 0, and we're asked what are the readings on the other 2 clocks, and then we have the same question in Bob's frame. Well, so let's get right to it. I'm going to keep the question here, but shrink it and put it up in the corner. Great. And we'll start in the beginning. We'll start with part A. We want to draw a diagram of the situation from Alice's frame and then Bob's frame. So let's do Alice's first. In Alice's frame, which is also the ground frame, and I'm always, when I draw my diagrams, I'm always going to label my frames and be really explicit about that. In Alice / the ground frame, we have the following. We have the ground, okay, and we have Alice, and she's at rest. And then we have 3 clocks, A, B, and C. And remember, I'm going to use this diamond symbol for my clocks. And these are all at rest. So we have clocks A, B, and C. Okay. And then we have Bob. He's moving to the right. So we say running, but all that really matters is he's moving. And his speed is 1/5 C, whether he's running or floating or in a rocket, it doesn't matter. But he's moving to the right at 1/5 C. Everything else in this picture is still because we're in the ground frame and Alice and the clocks are at rest in that frame. Okay, so we'll repeat in Bob's frame. We'll repeat the snapshot diagram in Bob's frame. We'll just call it Bob's frame. Bob's frame, okay. And the number one thing that you can remember when drawing these diagrams is in Bob's frame, Bob isn't moving. In Alice's frame, Alice isn't moving. In frame X, object X is not moving. So we got to make sure that no matter how we draw Bob, we got to make sure that he's at rest because it's his frame. And a person is always at rest in their own frame. And then we have these other objects, right? We have Alice, and we have these 3 who I recognize. I have clock A and I have Alice A. So I'll just write out the word Alice to differentiate between clocks with the name A and a person whose initial is A. We have clocks A and B and C. These clocks, though, are all moving. And they're all moving to the left. And they're all moving at the same speed. And Alice is included in that. Every object, except for Bob in this picture, is moving to the left at 1/5 C. And remember, how do we know that it's moving to the left? Well, if in Alice's frame, Bob's moving to the right, then in Bob's frame, Alice is moving to the left. That's reciprocity. Vxy equals minus Vyx. So just to be really explicit on that we have V of Bob relative to Alice is equal to minus V of Alice relative to Bob. That's reciprocity. Okay, so we're done with part A. We've drawn the diagram in these 2 frames. We can move on now to part B. And in part B, we are told that clock B reads 0. What are the readings on clocks A and C? So this is Alice's frame. Okay, so if we'd like, we can just duplicate this picture. We'll bring it over, okay? We have clocks A and B and C, and we're told that clock B reads 0. Okay. Oh, sorry, I should go back to part A and make sure that I label some relevant quantities here. So we know that there's a 30-foot gap between A and B and a 60-foot gap between B and C. Now, we haven't covered length contraction yet, but what we're going to see is that moving objects are shorter than those objects at rest, and that includes the gaps between objects. So although A and B, clocks A and B, are 30 feet apart in the ground frame, when A and B are moving, they are less than 30 feet apart. We haven't quantified how much less, but for now I will just write less than 30 feet. And then similarly, this separation will be less than 60 feet. So it would be incorrect to label the gaps in Bob's frame as 30 and 60 feet. That would be incorrect. But in Alice's frame, the gaps are 30 and 60. So I can copy that over here. Okay. Now this part of the question, what are the readings on clocks A and C, in Alice's frame is a straightforward question, right? Because in Alice's frame, all of the clocks are at rest, and we are going to always assume that clocks that are at rest in the frame of reference that we're drawing, if they're at rest, they all have the same reading, even if they're separated by some space. So all three of these clocks are going to have the same reading. Okay? So that's just by the definition of synchronized clocks. However, part C is asking us to do the same thing in Bob's frame. And what we're going to see is that in Bob's frame, these clocks are not reading the same number for a single instant of Bob's time. Okay? So let me, what am I going to do here? Make some space. Will this all come? No, this one will come. Okay. So what we're going to do is we'll just use this diagram down here on the left, because that is the drawing in Bob's frame. So here we go. We're going to be focusing down here. And the first question is, which is the rear clock? Okay. Well, we have three clocks. Okay. So the rear clock is the one that reaches Bob last. So A gets to Bob first, then B would get to Bob, and then C would get to Bob. So we would say that C is rear to B, but B is rear to A, and it's also the case that C is rear to A. Okay. And if we know that the reading on B is 0, then we know that the rear clock is set ahead. So a clock that's rear to B, clock C, will have a larger number than 0. But B is rear to A, so that means the reading on B has to be larger than the reading on A. So for 0 to be larger than some number, it has to be that other number would be negative, right? So just to throw a number out here, if A were -1, then B would be 0, and 0 is bigger than -1. And if C were 2, then C would be bigger than 0, 2 would be bigger than 0, and 2 also would be bigger than -1. Okay, so if you remember, RCA, the rear clock ahead, the amount of the rear clock ahead is LV over C squared, where the relevant length L is the rest frame separation of the clocks, so the 30 feet for A and B, or the 60 feet for B and C. I've copied our Bob's frame diagram onto a new page to give us a little more space to work with, and I've reminded us that the RCA equation for how much time difference exists between two clocks is given by L naught V over C squared, where C, the speed of light, is 1 foot per nanosecond. And I'm reminding us that the separation in space between B and C is 60 feet in their rest frame, L naught being the rest frame separation. And the separation between A and B is 30 feet, again, in the frame where those objects are at rest, in the ground frame, also known as Alice's frame. So let's start by computing the reading on clock C, given that the reading on clock B is 0. So we'll say reading on clock C is larger than that of clock B by L naught V over C squared, where here L naught is that 60-foot separation. So we have L naught V over C squared is equal to 60 feet times 1/5 of the speed of light, 1/5 of a foot per nanosecond, divided by 1 foot per nanosecond quantity squared. Okay. If we now look at the units, we have feet times feet divided by feet squared. So feet will cancel. And if we also look at the units of time in the denominator, we have 1 over nanoseconds squared, and in the numerator, 1 over nanoseconds. When you take that ratio, you're going to get nanoseconds to the first power. Okay, so we have a unit of time as our result, which is good because we're looking for a set ahead time. The only remaining item here is to recognize that 60 divided by 5 is 12. So we just need to write our number 12 here. And that tells us that the reading, just to be really explicit here, the clock C reading, right, is equal to the clock B reading plus 12 nanoseconds. Well, the clock B reading is 0. So in this case, the set ahead amount is also equal to the reading on that clock. That's not in general true, but in this example, that is true. So here, the reading that goes in here would be 0 plus 12, which is 12. Okay. So the next thing we can do then is calculate clock A, given the reading on clock B. And what do we know about the clock A reading? Well, we know that the clock B reading is bigger plus it's bigger by L naught V over C squared, right? Because B is rear to A and the rear clock is ahead. Okay, so what that tells us is clock A reads smaller than 0. That's the reading on clock B by L naught V over C squared. And this time L naught is not 60 feet, but rather 30 feet. That's the rest frame separation between A and B. Okay, so we have L naught V over C squared is 30 feet, 1/5 foot per nanosecond divided by 1 foot per nanosecond squared for the speed of light. But we can also recognize that everything in these two calculations is the same except the length is half. And so what we know is that the answer will be half. So instead of 12 nanoseconds, we're going to have half of that, or 6 nanoseconds. So clock A reads 0 minus 6 nanoseconds. So it's the clock B reading with but smaller than that by the RCA. So the reading on clock A is going to be minus 6 nanoseconds. So the reading on clock A will be 6 nanoseconds less than the reading on clock B. So 6 nanoseconds less than 0 is minus 6. And that minus 6 came about as 0 minus 6. Great, so we found the readings on the 3 clocks. One thing we can do, though, is do a little cross-check, right? We calculated the reading on C and we calculated the reading on A using offsets relative to the clock B. But let's also check that if we looked directly from A to C, that we would expect that they read different numbers by 18 nanoseconds, right? 6 less than 0, 12 above 0 is a difference of 18 nanoseconds, sorry. So let's do that calculation. Okay, so let's look at the RCA from A to B. Okay, they're separated by a rest length distance of 30 feet plus 60 feet, or 90 feet. Okay, and they're moving at 1/5 C. So the RCA between clocks A and C is equal to L naught V over C squared, or 90 feet times 1/5 C, 1/5 of a foot per nanosecond, divided by 1 foot per nanosecond quantity squared. And we have 90 over 5 is 18 nanoseconds. Okay, so clock C should be bigger in its reading than clock A by 18 nanoseconds. And what did we find? We had calculated -6 and +12. Okay, so 12 is equal to -6 plus 18, indeed. So that checks out. So great. So in this video, we got a little bit of practice using RCA to calculate the reading on one clock given the reading on another clock and given their rest frame separation. And, that's great. We know how to do the calculation. But let's not lose sight of the main idea here, which is in the ground frame where all three clocks were at rest and so was Alice, all three clocks had the same number on them, the same reading, at a single instant of time as measured by Alice. However, in Bob's frame, which is what's drawn in this picture here, the same three clocks all have different readings on them at a single instant of Bob's time, right? So this is a snapshot diagram in Bob's frame, so it represents a single instant of time in Bob's frame, and yet at that one instant of time, these three clocks all have different numbers on them, even though when clock B reads 0 in Alice's frame, the other clocks A and B also read 0. So that's one of the bizarre consequences of relativity, that clock readings are not necessarily simultaneous. They don't all read 0 at the same time in Bob's frame, even though they do all read 0 at the same time in Alice's frame. All right, friends, until next time, be well.